So now I think we're going to turn to our last talk by Meredith MacGregor, our last talk of the session. Meredith MacGregor is an assistant professor in the Department of Astrophysical and Planetary Sciences at the University of Colorado Boulder. She received her BA, MA, and PhD in astrophysics at Harvard. Dr. MacGregor's research group uses multi-wavelength astronomical observations to explore the formation and habitability of planetary systems. This area of research has become increasingly important. And I understand this area, the search for habitable planets, now represents a major effort in the new decadal survey of the astronomical community, which was just announced this week, where they set the priorities for astronomers in the United States for the next decade. Her work on the search for habitable planets has been widely covered in the popular press, including Scientific American, Science News, National Geographic. Professor MacGregor is the co-chair of the NASA Infrared Science Interest Group Leadership Council, member of the Origin Space Telescope Disks and Planet Formation Working Group, and the associate director of the Center for Astrophysics and Space Astronomy. The title for her talk today is How to Form a Habitable Planet. And I'm delighted to turn the podium over to her.
Wonderful. Thank you, Jackie. Let me go ahead and share my slides. I can't give an astrophysics talk without showing beautiful images. So I'm going back to the slide deck. Great. So today I'm going to talk to you about how we form a habitable planet. And before I kind of delve into the science too much, I want to give some background. Since not everybody here is an astrophysicist, we don't all think about this every day. So how do stars and planets form? We think our picture of this is that we start with a giant molecular cloud, this swirling cloud of dust and gas in space. Pieces of that cloud increase in density, and eventually they become dense enough that they'll actually collapse under their own gravity and form a new baby star. And that star is then surrounded by a disk of swirling dust and gas, which is what we call a protoplanetary disk. Protoplanetary being the place that planets actually are born. So this phase of star and disk evolution lasts for about somewhere between 1 and 10 million years. Eventually, that remnant disk is cleared away for the most part, and what we're left with is a main sequence star, a star during the main part of its lifetime, any planets that might have formed during that earlier phase, and sort of leftover remnant material. And this is how we think we form planets. So what does it mean when we talk about habitable planets? So astronomers often invoke a very simple definition for habitable planets, which just says, defines habitability based upon the distance a planet is away from its star. And we define this based upon how we understand life on Earth. We humans are water-based. Everything on Earth uses water. And so we assume that water must be critical for life. And then we define a habitable zone based upon how far can I move this planet away from the star and have it be at just the right temperature that there could be water on the surface of this planet. If I move the planet too close to the star, it gets too hot, the water will evaporate. If I move the planet too far away, it's going to get too cold, the water is going to freeze. So you end up defining essentially a Goldilocks zone around a star where a planet can be, and we can have liquid water allowable for Earth-like life. But that is simplistic in many ways. And if we really want to have a better picture of habitability, then we need to complicate things, because there are many other factors that might influence whether a planet is habitable or not. Our Earth has a molten core, which allows us to have plate tectonics. And plate tectonics allow us to have climate circulation, which pulls CO2 out of the atmosphere and into the plates, into the Earth's crust, right? The size of our planet allows us to have a liquid core, whereas Mars, a smaller planet, does not. I might also care about what the star is doing in the system, what the other planets in the system might be doing. I might care whether my planet is rotating. I also might care what's even in its atmosphere, right? Do I have volatiles, things that allow us to have life, things like carbon monoxide, carbon dioxide, methane? All of these, right, are a huge amount of things that go into forming a habitable planet. And so what I want to talk to you about today is how we can step away from that typical Goldilocks zone and start thinking about at least a few of these factors that might influence whether a planet is habitable or not. So I'm going to start with two of them at the same time, which is the first question, do other planetary systems have outer giant planets? And then how are planetary atmospheres formed? And on this slide, I'm showing a picture of our planetary system. And we have a pretty, regular architecture to our system. We have our sun, right? And then we have 4 inner planets. They're all sort of rocky, small planets. And we have 4 outer planets, which are much larger and dominated by gas and ice. And we think that actually these outer planets played a pretty critical role in the evolution of our solar system, and that they both stirred up material in that original disk to cause collisions that actually delivered water to Earth, and that they then stopped future collisions, which allowed Earth to be a stable environment for life to exist. So how do we detect exoplanets? On the left, I'm showing the 3 main ways that we've detected exoplanets to date. So the first is what we call the transit method, where we're actually looking for a planet to cross in front of us. And when the planet does that, if we measure the total brightness from the star, we see a dip, which is light being blocked by that planet crossing in front of it. We can also look for a shift or a wobble in the star itself due to the gravitational tug of a planet on the star. That's what we call the radial velocity method in the middle here. And the bottom panel is showing direct imaging, which is where we actually use something called a coronagraph to block the light from the central star and then image the planets surrounding it. And on the right, this is sort of the population, the zoo of exoplanets that we've found to date. And I'm showing period on the x-axis, so how far basically away that planet is from the star, and mass, the size of the planet, on the y-axis. And for illustrative purposes, some of our solar system planets are here. We have Earth, Jupiter, Saturn, and Uranus. And when you look at this plot, you might notice a few things. One is, we're not really sampling where our planets are in our solar system, right? There's a huge hole here. I can't actually tell you today whether planets like Saturn or Uranus are common at all, because our techniques that we used are inherently biased, right? I'm looking for things to orbit a star multiple times, and that's very good at detecting things that are close to the star, but not very good at detecting things that are farther away. So we need to do some work to put our planetary system in context with exoplanetary systems. And one tool that I've been using to do this is something called the Atacama Large Millimeter or Submill Array, which is what we call ALMA. So ALMA was built a little over a decade ago, and it's a radio interferometer. So this is ALMA radio telescopes down in the desert in Chile. This is in the Atacama Desert in the kind of high altitude plateau of Chile. And ALMA has completely changed how we look at planetary system evolution and formation. So here, just so for context, this is shows here in the purple box where ALMA actually is in Chile. This is at about 17,000 feet of elevation. Here's a zoom in of the actual antennas at the ALMA array, so you can see more of what this telescope looks like. These are large radio dishes. And an important point about ALMA is that these antennas can actually be rearranged. So we can drive up to these antennas and scoop them up with this big caterpillar and then drive them to different locations across this plateau. And we can move the antennas around in order to get better imaging, basically. If I move the antennas farther apart, I get higher resolution. I can look at more detailed structure in my images. And so before I came to see you here, I was at the Carnegie Institution in Washington, DC. So this is a DC-centered view of the ALMA array. If I take those radio antennas and I move them the closest that I can possibly move them, I'll take 66 radio antennas and put them in the ellipse of the White House here on the right. The left. And if I move them as far apart as I possibly can, so I want to get the best image, the highest resolution, then I'm moving the antennas to span the entire beltway in Washington, DC. Okay, so what can we do with this amazing facility? Well, I forgot I put this in here. I wanted to show exactly what this means in terms of wavelengths of light. So we as humans observe in what we call visible light, which is a very narrow part of what we call the larger electromagnetic spectrum. And so light actually can have much longer wavelengths where I move the peaks of the light further apart, or much shorter. And ALMA is over here on sort of this left side of the plot where we're looking in what we call millimeter wavelength light. So the space between the light waves is actually about a millimeter. And this is where we're actually seeing material around these stars, dust and gas, getting heated and glowing as heat, essentially. So with ALMA, we can image these environments where planets are forming. So I can go and take beautiful images of disks where I think planets are actually forming now around young stars. And when we do that, we find that there's a lot of very weird structures. They don't look very regular. So here's two different disks, and they're actually eccentric. Eccentricity means that the orbits of the planets are actually elongated. They're elliptical instead of circular. And you can see that visually. If this was a circle, the star should be at the actual center of the disk, which is marked by the pink X. And instead, the star is actually offset visually, which indicates that this disk is significantly eccentric. And a logical conclusion here is that maybe it's a newly formed planet sitting on the inner edge of this disk that's actually, sculpting the material on this disk, carving it out in order to make it this eccentric shape. And I can do even better than that. These are higher resolution ALMA observations of the same disk. Now just looking at both this side over here and this side over here, what we call pericenter and apocenter. And I predict that if it really is a planet that's sculpting this disk, the width of the disk should vary as a function of azimuthal angle around the disk. So it should be fatter at one side and narrower at the other. And ALMA actually allows us to resolve that. We can see this difference in the width of the disk on different sides of it. And I can then use those structures to place constraints on the planets, right? I can model the structure of these disks, and then we can place constraints on what the mass, the orbital properties are of these planets that we're not seeing so far. So this is an example on the left. We have 4 planets that we've actually directly imaged. So you can see these planets orbiting in this image, and they're sitting inside of a giant ring of material, which is imaged here. And on the right is a different example. This disk actually has a gap being carved out of it by a planet, and we can model that to be, a roughly Jupiter mass planet sitting inside of the disk. So if I follow that through, right, and I look at all of the disks that we can image with ALMA, that we have looked at with ALMA, we see a lot of structure. Almost every disk has rings and gaps and asymmetries in it. And so there's now maybe a zoo of other planets, right? If I do the same logic here, I image all of these systems, I model what kind of planets could be in those. Now I'm coming back to this same plot. We're showing planet mass as a function of semi-major axis, again, distance from the star. And now instead of having a hole on the right-hand side of the plot, I have a whole population of planets. The same planets are the gray dots that we're finding through our other detection methods. And all of these colored symbols are the planets that we are inferring by looking at the structure in these disks. So I think this is potentially a really exciting space to be able to start to put our own solar system into context. Okay, so a last note on disks, of course, is so far I've only shown you structure, right? Actual material being carved by planets, gravitational dynamics. But there's a lot more going on in disks. So this complicated figure is attempting to convey that by showing on the left sort of an early disk where planets haven't formed yet, what we call a protoplanetary disk, and on the right a more evolved disk where it actually formed a few larger planets, what we call a debris disk. And you can see an immense complexity in terms of chemistry. We have ice and dust and gas all coexisting in these systems. And different telescopes actually allow us to look at different radial distances. So ALMA, which I've been talking about so far, is really good at sort of distant planets, right? It's probing things like Jupiter and Saturn and Uranus. If I want to look closer in, I might need to complement that with other instruments. Something like the JWST that's going to be launching in December is going to allow us to actually image disks, but further in and closer to the star. And ideally, we would be able to use all of these facilities to actually trace how dust and gas is moved through the planet formation process and then inherited into the atmospheres of exoplanets that we see today. Okay, so changing directions a little bit. In the middle of all of these disks and planets is a star, right? The center of our system is a star. And stars are very interesting and potentially have a role to play in habitability. So stars are what we call active, and our sun is active as well. And that means that stars actually send out bursts of radiation, which is what we call a flare. So when a star flares, it throws out X-ray UV light into space. And then it's sometimes also accompanied by something we call a coronal mass ejection, or a CME, which is a release of charged particles. So that radiation and charged particles travels out into space, and it then hits any exoplanet surrounding it, right? And hits the atmospheres. And that radiation and particles can get into the atmosphere, and it can actually start to dissociate, split apart molecules like water and ozone in those atmospheres. Now, this happens in a much more extreme sense in exoplanet systems, but it also happens on Earth. Our sun sends out flares and CMEs, and those are what are responsible for the beautiful auroras that were in the news recently, because that's atoms and molecules getting split apart in the atmosphere of Earth and then glowing, producing beautiful aurora, but also indicating that we have an active star as a neighbor. So I've been studying a different stellar system, which is Proxima Centauri. So Proxima Centauri is the closest stellar system to us. And it is what we call an M-dwarf star, which means it is a smaller and cooler star than our own sun. And it's surrounded by 2 exoplanets, one of which, Proxima Centauri b, is roughly an Earth mass and sitting in that Goldilocks zone. It's at a distance where we think it could have liquid water. So it's an excellent test case to look at how the star might impact planets, because it's kind of the best system we have to think about and possibly look for life in the universe. So in order to study the star, I carried out a multi-wavelength observing campaign. So we spent about 40 hours observing Proxima Centauri simultaneously with these 8 different telescopes. And the goal here was to cover the entire electromagnetic spectrum that I showed you earlier, because stars flare across the entire spectrum. And in order to understand the energetics, we want to see weight at all of those wavelengths. So we used ALMA again, and then several ground-based optical telescopes, the Transiting Exoplanet Survey Satellite, or TESS, in space, the Hubble Space Telescope, SWIFT, and Chandra. And that spans everything from the radio wavelengths through the optical, the ultraviolet, and the X-rays. And when we did this, we found some really exciting things. So far, we've detected the largest flare that's ever been observed from Proxima with both Hubble and ALMA. And what I'm showing here is a light curve, which is how we see flares from stars that are far away. We can't resolve stars with our telescopes, and so we see the change in the total amount of light from the star. So this is median normalized flux. So it's basically showing how much does the flux of the star increase during the flaring event. And then this is in time on the x-axis. And it's stepping in wavelength. So we have ALMA at the top here, TESS, one of these optical telescopes on the ground, and the Hubble Space Telescope. And so you can see that we're going along. The star is doing its normal quiescent thing, and then it flares abruptly. And what's really neat about this data is that for the first time, we actually have wavelength coverage. So we can see correlations between different wavelengths, which is something we've never been able to do before. So the millimeter and the UV data, as traced by ALMA and Hubble, which is zoomed in here on the right, trace each other incredibly closely. They look like the exact same event, and they brighten by a huge amount. The ALMA flux brightens by a factor of 1,000, and in the Hubble data, the flare brightens the star by a factor of more than 14,000 times, which is astounding. And the entire event only happens for 7 or 8 seconds. So the star increases by a factor of 14,000 in brightness in 7 seconds, and then it goes away back to nothing. The optical light is actually delayed. So you can see where the peak is here actually quite a bit after, and it's at a much lower level. So we're really seeing there's this kind of decoupling between light at different wavelengths. And what I think is really exciting is that this could be a way to probe the high energy environment of planets, because it's ultraviolet light that does the most damage to atmospheres. And unfortunately, the only way we can see ultraviolet light right now is with the Hubble Space Telescope. And it's hard to use a space telescope, but we can do millimeter observations from the ground. So if this proved to be a real correlation, we could use radio and millimeter observations to actually then say and infer what the ultraviolet light is from these planets, and then understand what's happening to the exoplanets that surround them. So to show that this isn't insane, on the left is another flare, right? So I'm showing you one flare that lasts 7 seconds before, but we observed for 40 hours. So we saw many more flares. So this is another flare here that shows the same behavior between ALMA and Hubble, and now adding in SWIFT ultraviolet data as well. But this is all still for one star. So what I'm starting to do now is to do a survey of sort of our nearest stellar neighbors. So this is a plot showing our sun at the middle, and then all of the nearest stars surrounding us. And in orange, I'm highlighting the stars that we're sort of initially tackling in this new campaign. So we've done Proxima, and now we're going out to look at 4 more stars with ALMA and a suite of other telescopes to try and do the same work and really constrain the radiation environment of these nearby, potentially exoplanet host stars. Okay, and then I think where this needs to go next is that we need to take this even another step further and really think beyond just basic astrophysics. We need to understand what a flare like this would do to an atmosphere. So this is a simulation showing what happened to Mars in our own solar system, which had its atmosphere stripped by the sun. So we need to model the atmospheres of these planets, right? We need to turn this astrophysics data into real models of atmospheric erosion, changes in composition, trying to understand what the chemistry is happening in these atmospheres when an event like this happens. And then I think we need to take it even further into biology and look at what happens to life. So this is some new work that we're just sort of toying around with and getting started with, which is to actually take the spectrum of one of these flares, consider, the amount of UV light that's going to reach the surface of a planet that would be impacted by this flare, test this in the lab, and really, try and see if I put this much UV light on something, what's going to happen to DNA. And then look for these sort of breakage patterns in DNA to understand even the possibilities for having life survive on a planet like Proxima Centauri that's orbiting an active star. Okay, so I hope that I have convinced you that habitability is a complicated topic. It depends on all parts of planetary systems. We can't understand the habitability of a planet unless we look at the planet and the disk that it grew out of and how it affects that disk, and the star that's in the center of all of it and how the star might change the chemistry, the dynamics, everything about this system. So I will come to my concluding slide here and say that I think we're in a really exciting time here. We have amazing new observational facilities, and they have completely revolutionized how we understand the formation and evolution of planetary systems. And then with that, we need to work in an interdisciplinary way to start thinking about planetary habitability. And my hope is that through this kind of work, we'll further constrain what actually makes a planet habitable. We'll move beyond that simple definition, and that will inform our searches for life elsewhere in the universe. And with that, I'm happy to take any questions.
Thank you, Meredith. That was terrific. You've got several questions already. So let me start with Richard Schifrin, who says, what sort of physical process can cause a 14,000 times increase in brightness for only 7 seconds and then cease quickly?
Yes, that's an excellent question. So the picture that we have of stars is that the interior of the star is actually convecting. And so you have a picture where you have a star and it has internal convection, and then it has a magnetic field that actually threads through the surface of the star. And as the convection happens, those magnetic field lines actually twist. And so they twist up, kind of knot themselves together. And eventually there's too much tension, and we think that the magnetic field lines snap and then reconnect. And it is that dramatic breaking of a magnetic field line that actually produces the flare. So it releases this huge amount of energy. And the charged particles that we see are actually getting, spiraled around those breaking magnetic field lines and then flung outwards into space.
Thank you. This is an interesting one. Thomas Klein, do you know if an ocean would protect life from these huge UV bursts?
Yeah, so that's an excellent question and point. So the ocean and on Earth, we think that life originally formed probably underwater, right? Because water, like an atmosphere, is very good at protecting from UV radiation. And early Earth didn't have ozone in the atmosphere, which is what protects us now, right? We didn't actually have oxygen or ozone until much later. And so you needed to have life form underwater probably, and then slowly move on to land as the oxygen content in the atmosphere built up. So it is possible, to imagine a planet with a thick ocean on it that might still have life, even though it's hanging out really close to a star that's throwing out angry bursts of radiation. But things get even more complicated, because one of the things we think is that if you take one of these planets, they're so close to the star that they might actually be what we call tidally locked, which means that one side of the planet faces the star at all times. And so the planet isn't actually rotating as our Earth is, right? Our moon is actually tidally locked to the Earth. And so then maybe without rotation, you don't have a magnetic field, which means you can't protect an atmosphere. And then how do you have an ocean without an atmosphere? So there's a whole lot of interconnecting pieces that we need to figure out in order to really think about this.
Gotcha. Thank you. Let me ask, let me ask a two-part question. One from David Tattle, and also from Rowena Matthews, and they're really related. First, Rowena asks, is it necessary to assume that all life must be water-based? And then Tattle asks, more generally, in the search for habitable planets, how are you defining life?
Yeah, that's an excellent question. So far, we have absolutely done the strategy of, we know of one place in the universe that has life, and that's the only life that we know about, right? And so we think of life as what is on Earth, but there is no real rule in the universe that says that's the only way to have life. So, you know, chicken and an egg problem here. If I open it up that we can look for anything, then I also don't know what I'm looking for, right? And so someplace, you know, by basing it in Earth-like life, then I have a standard that I can, you know, apply other places and look for characteristics that I think are important. And if I say, you know, maybe life could be based in silicon instead of carbon, then it's hard to know, like, what are the biosignatures you're actually searching for at that point. But the universe is a big place, probably will surprise us.
Certainly will surprise us. Sarah Seeger asks, with your new work, can we better estimate the total energy from a flare using only optical data? E.g., people claim that a TRAPPIST-1 star flare was equivalent to the Carrington event, but only with extrapolation.
Yeah.
Maybe you can explain that a little bit too.
Yeah, so what we've typically done when we study flares is that we look with only one telescope. And so we see the flare happen, but we see it only at one wavelength of light. And that's, I mean, we can still tell that there's a flare happening. We can tell how bright it is in that one wavelength, but we don't know what the spectrum is, you know, how it's behaving across all of those different wavelengths of light. And in order to get like the true energy budget, you need to know what the entire, you know, energy is of the flare, which means we need to look at different wavelengths. And it's been very hard to do that sort of multi-wavelength work. I can tell you from personal experience doing this project that the only way this happened was essentially an email chain of me and like 8 different telescope schedulers trying to coordinate when we were going to have the telescopes look at the same time. It's not easy. And so we haven't gotten a lot of data sets like this. And my hope is that this will make that easier because we can have a sample of flares now, a significant sample where we've seen it at many different wavelengths, and we can start to really derive those scaling relations. And so that's why I think if I just, you know, pop back here quickly, from a like wavelength perspective, I'm really excited by the fact that the ALMA and Hubble data trace each other well. Traditionally, we've always used optical data, and actually, if you scaled this optical data, and it's so decorrelated and at a much lower level than the Hubble data that it would not have produced kind of, we wouldn't really have any idea if we use typical scaling relations. In fact, like this flare is so small in the test data that like 75% of the flares detected by tests from Proxima are bigger than it, but it's 14,000 times brightening in Hubble. So I think that suggests that, you know, scaling optical to ultraviolet might not be the best, and that maybe something like the millimeter is actually a better tracer. But we'll learn that, and then that will better inform, you know, our future work.
Right. Let me ask one last question. How concerned should we be? This is from Frank Stewart. How concerned should we be about the possibility of another CME on Earth of roughly the magnitude of the one in 1859? Should we be preparing for such an eventuality? And if so, how?
Yes. So I've gotten this question before. Yeah, it's an interesting question. You know, in general, I think we're pretty lucky because our sun is a relatively quiet star. It throws out flares and CMEs, but they are, for the most part, not enormous. And they're certainly not large enough to be, you know, stripping our atmosphere away. So that might be something that is good for a habitable planet, right? You want planets around relatively quiet stars. That being said, the sun definitely still throws out flares and CMEs, and we could, it's, you know, well within likelihood that we could see another event of that magnitude. In terms of effect on Earth, people study this, and generally what I've seen is it predicts that you have a lot of disruption to power grids and like communication satellites, and it would be, you know, not the best for our modern society, but it also wouldn't, you know, kill life on Earth.
On that note, let me thank you again, Meredith. This was just terrific. And let me remind everybody that we have a wonderful concert at 7 o'clock Eastern time. So please come back and join us. And let me thank all the speakers in this session for their outstanding presentations. I certainly learned a lot. I'm sure everyone else did as well. So thank you all very much.